Hi and welcome to another lesson in the memory series. Today's topic is memory ideas. Objectives of this lesson. We will see examples of interesting memory constructs. To be specific, we are going to see three examples. Array of structures, two-dimensional table, and binary tree. The memory is not just bytes. It is made of bytes, but don't let it limit your thinking. Big ideas could be implemented with those little bytes. And what do I mean by that? So far we've seen that the memory is just a very simple construct. It is just a linear array of bytes. And you might be disappointed about it. Don't let this confuse you. The fact that this construct is very simple doesn't mean that you cannot do complex things with it. In fact, you can really do anything that you want. It is just about imagining it and figuring out how to take your idea and flatten it into the linear memory. I begin with the very simple idea of array of structs. For example, I want to have an array of dogs, where a dog is defined like this. It is a simple structure. Two fields of size d word each, which means that it has a total size of 8 bytes. So how can I define an array of this kind of structs? The simple solution is as follows. Let's, for example, denote the number of dogs that I want in my array to be 12. This is a constant definition. FASM supports this kind of constant. I declare inside the BSS section the following. My dogs is going to be the label that marks the location of the array construct that I'm going to declare. And then I'm going to allocate num dogs times size of .dog bytes. What does that mean? It means that I know that every dog is going to take size of .dog bytes in memory. So if I want to allocate num dogs, then I have to multiply those two amounts to calculate the total amount of bytes that I have to allocate. In this example, num dogs equals 12, and the size of the dog structure is exactly 8 bytes, which means that the total size that I have to allocate to have an array of 12 dogs is going to be 12 times 8, which is 96. So this is going to allocate 96 bytes in the BSS section. 96 raw bytes. They don't have anything special about them. The only thing that is special about those bytes is the way that I think about them and the way that I use them with my code. Besides that, those are just 96 bytes. Nobody knows what those bytes are, especially the processor. The processor cannot understand that this is an array. It is not that complex. The processor is a very simple creature. It can only understand lists of bytes. It can only understand the usual representation of memory that we have talked about. Let's look, for example, how can we access dog number ECX. Let's assume, for example, that some code initially filled in the myDogs structure, because we can see here that it was defined in the BSS section, which means that it is uninitialized. We can see here that it was declared in the BSS section, which means that it is uninitialized. So assume that some code here has already initialized this memory construct. And now we just want to access dog number ECX. Maybe we got ECX as an input, for example. Maybe the user wants the details of dog number ECX. So how can we get the details? We first load the label myDogs into ESI. And then we want to calculate the location in memory, the exact location in memory of dog number ECX. And this is just about simple math. All that we are going to do is take the base, which is myDogs. This is where the array begins in memory. and we add it to ECX, which is the dog index or the dog number, times size of dog. Which means that if we want the first dog, which is of index 0 because we begin to count from 0, then the resulting address is going to be ESI, which is the location of the first dog, because the first dog is exactly in the beginning of the my dog's memory location. This label is exactly on the first dog. If we want the second dog, then ECX is 1. So we get the resulting address of ESI plus 1 times size of dog. If we want to access the second dog, we have to assume ECX equals 1, which means that the resulting address is going to be ESI plus 1 times size of dog, which is going to be my dog's label plus 1 times 8, which is just the my dog's label plus 8, which is the location of the next dog, because the first one takes exactly 8 bytes. So the next one is going to begin from my dog's plus 8. Finally, after we got the address, the exact address of dog number ECX, we can access its fields or its attributes. We do it like this. We just take ESI, which is exactly the location of this dog in memory, and we add dog.color or dog.age. And we can use those addresses to read the corresponding D word to color or age. So this is how we access one element of an array of structs. Higher dimensions. Assume that we want to remember the multiplication table in memory. And I mean in the computer's memory, not in your memory. I remind you how the multiplication table looks like. This is something that you have probably learned in elementary school. There are a few rows and columns, and every number, for example 6, is the multiplication of 3 and 2. We know how to generate every cell. It is just the multiplication of the row number and the column number. And in this specific example, we begin to count the rows and the columns from the number 1. So this is the question: how can we store a two-dimensional object in our one-dimensional memory landscape? This is a pretty important question. Many high-level languages have just some kind of a built-in multi-dimensional object that you can define, but this is not the case in assembly language, as you have probably guessed. You have to do it yourself. So how can we do it? We use our imagination. Let's look at an example. There is some modification to the previous table that you have seen, because this time we begin counting from 0 and not from 1. This is how we do it in assembly. We begin usually to count from 0. This is just to make the calculations a bit easier. This is one way of taking the two-dimensional object, this table, which is 4 over 4, and flattening it out into the linear memory. This is the picture in the linear memory. This is how the processor sees it. And this is how I imagine the data. There is no table. It is just in my imagination. The way that the memory is ordered is just like this. Just a set of 16 consecutive bytes. However, I imagine those bytes as a table. The colors that you see here should help you understand which byte corresponds to which byte between the linear memory and the table. For example, this cell corresponds to this cell, and this cell, number 11, corresponds to this cell, number 11. This is just one way to do it. We could do it in some other way, or even many other ways. Some important thing to keep in mind when choosing some way of representation is that we want to be able to transform easily from the linear memory representation to our representation. Here we do have a way to do it. Let's look at an example for the cell in row 3 and column 1. This is row 3 and column 1 is here. So we are talking about 7. It means that this cell is represented by cell number 7 here. So we have some kind of rules that allows us to understand which byte corresponds where. This is about how we calculate it. We just take 1, which is the column number, and 3, which is the row number, and we use this formula. 1 times 4 plus 3 equals 7. This is our formula. And maybe generally how to calculate the location in linear memory of some cell. If we talk about the cell in row R and column C, then we know that it is in location C times 4 plus R. Where does this formula come from? Well, we could infer it just by trying some things. We can just look at those cells, and the numbering here inside those cells actually corresponds to the linear numbering. We can just look for some kind of a rule, and we can see that whenever we move to the right, the number is increased by 4. And whenever we move down, the number is increased by 1. So this kind of formula makes sense. There are more ways to infer it, but this is the really simple way to do it. Just to notice that whenever you move to the right, the number increases by 4, and whenever you move down, the number increases by 1. This is another way to represent this table. It is pretty much the same thing. It is just a different orientation. This is also known as transpose, the transformation that we've just did from the previous table to this table. Just to remind you the difference, let's take a look again. This is the first representation of the table as a linear bytes array, and this is the second representation of this table as linear bytes array. The numbering on the bytes array hasn't changed. We always refer to byte number 0 as 0 and byte number 15 as 15. The only thing that have changed is the way that we think about those bytes. This is what we see in our imagination, and this is the only thing that have changed. The fact that we use 16 consecutive bytes on memory, it hasn't changed. Only our imagination has changed. In this example, we can see that whenever we move down, the number increases by 4, and whenever we move to the right, the number increases by 1. So maybe just as an example, let's take a look at location 13, which is also here. It is the cell in row 3 and column 1. And indeed we get 1 plus 3 times 4 equals 13. As a general formula, we get that the cell in row R and column C is in location C plus R times 4. What about the inverse transformation? Assume that we think about byte number 11. Byte number 11 in the linear representation. For example, this byte. And we want to know where can we find it inside the table. The inverse transformation is something like this. We just divide by 4 to get the row, and take the modulo by 4 to get the column. As an example, if we look on 11 here, then 11 divided by 4 is 2, which is the row number, and 11 divided by 4 and taking the remainder gives us 3, which is the column number. Generally, if we want to find k, we use those formulas. It is probably your job to think about it a bit more. I can't do it for you, but I just want to give you some kind of example to understand where do those formulas come from. Assume that you have a friend and your friend asks you to come over, and he tells you that he lives in apartment number 11. When you come over to his place, you find out that it is a building. It is not a private place. So you have to find his apartment. You see that there are many floors. And another thing that you find out is that in every floor there are exactly 4 apartments. How can you find the floor of your friend? The floor where he lives? Very simple. You divide 11 by 4. And then you find out that your friend lives in floor number 2. By the way, you can also know exactly where his apartment is going to be located inside the floor by taking the modulo. By taking the modulo, you know that his apartment is going to be in location 3 out of 4 in floor number 2. This is just an idea to think about it. You can just think about this table as a building with apartments. This is the general formula. Generally, you just divide by 4 to get the row, or the floor, you can call it the floor, and take the modulo by 4 to get the column, or the exact location of the apartment.